Fairly often, I get asked questions about how I got started podcasting with the Breaking Math podcast, and I'll often be asked this question by those who are thinking of starting their own podcast. That is, people who are looking to tell a story or share their unique wisdom with a larger audience or their passions, or maybe just advertise their business or services. I usually like to start this conversation by either showing off or telling about our preferred podcasting platform, Zencaster. Zencaster is essentially an all-in-one podcast hosting platform. On this platform, you can do everything from recording your episodes to editing your audio and video files to distributing your podcast to all podcasting platforms, including Apple Podcasts, Spotify, iHeartRadio, and wherever else podcasts are played. Now, there's more. When I first began podcasting, I used to get very nervous about how I would sound. I would sometimes stutter or have awkward pauses or other audio blemishes in my recordings. Now, Zencaster has a new suite of AI tools in their post-production process that make you sound really smooth. They automatically take out any of the ums or ahs in your recording. Also, they automatically take out any of the awkward pauses in your discussions. The tools will also help you set the right loudness and balance all the levels while reducing any background noise, all with the click of a button. Doesn't sound too bad, does it? You really should check it out. Really, the world needs to hear what you have to say. In fact, I'm going to give you a code below to help give you a large discount. It's all one word: Breaking Math. Go to zencaster.com/pricing and use my code BREAKINGMath, and you'll get 30% off of your first month in any Zencaster paid plan. I want you to have the same easy experience I do for all my podcasting content needs. It's time to share your
summer concerts, pool parties, chill nights under the stars. We're stocking up our closet so you're ready to look your best for all of it. At Plato's Closet in West Ashley and North Charleston, we're buying all things summer. So bring in your tees, tote bags, sandals, sunglasses, and more. We pay cash on the spot for gently loved name brand looks. Plato's Closet is the go-to destination for trend-forward teens and young adults who support local and shop sustainable. Visit Plato's Closet today. Plato's Closet, located in West Ashley on Sam Rittenberg Boulevard and North Charleston on Rivers Avenue.
I'm Sofía.
And I'm Gabriel.
And welcome to Problem Episode 8. Tangent Tango, where we're going to be talking about Morikawa's unsolved problem.
This was solved during the COVID quarantine. It's fascinating. I love the fact that people attempted these unsolved problems and they made some progress.
Oh yeah, there's been a weird, there's been a lot of weird academic stuff going on during COVID, and this is a pretty cool one. But before we start, we have a few plugs. So if you want a poster that has a lot of cool math diagrams on it that you can put on your wall, it's a 36 by 24 inch poster. We have one, and we are selling it on facebook.com/breakingmathpodcast for $19.65, which includes the shipping and handling, which is $4.50. You can get that at facebook.com/breakingmathpodcast.
Mm-hmm. And again, that's with it's a flyover of tensor calculus, which is pretty darn cool. It's the mathematics used in Einstein's general theory of relativity. So it makes a great birthday gift.
Oh yeah, and then we have our Patreon. If you want to support us monthly, it's just $1 or more. You could have our episodes with no ads and outlines. If you want to have updates about the show, you can find us on Twitter at BreakingMathPod or facebook.com/BreakingMathPodcast. We also have our website, breakingmathpodcast.app, which we're going to be updating pretty soon. And if you want to email us, just send us an email at breakingmathpodcast@gmail.com.
Yep, with any ideas, comments, or questions, or corrections. So without further ado, this problem comes from a type of math known as Sengaku, which has its origins in Japan. Basically, Sengaku consists of geometric arrangements, often involving geometric objects tangent to each other in artistic ways. And it was presented as gifts to Buddhist temples in Japan during the Edo period, which is basically between 1603 and 1870. Japanese math was distinct for quite a while.
For example, Seki Takakatsu, who lived from 1642 to 1708, was a Japanese mathematician who invented something very much like calculus, researched Bernoulli numbers, and this is all separate from the West. One thing about Japanese math is you have these sangaku, which they would put on, like Gabriel said, tablets and presented to Buddhist temples. And one example of this kind of problem is, let's say you have two rolling pins that are resting on a table of different sizes. if you want to squeeze in another rolling pin between them in the kind of triangular space between the table and the rolling pins, the size of that circle is given by 1 over the square root of its radius is equal to the sum of the inverse square roots of the 2 bigger rolling pins radiuses. That's a Sangaku, for example.
And today's problem is a specific Sangaku problem proposed by a man by the name of Jihei Morikawa in 1821. Sophia, would you like to explain this problem?
All right, sure. So let's say we have a line and you have 2 circles of any size resting on that line. So the 2 circles are touching one another.
And they don't have to be the same size circle, right? One can be larger than the other.
Yeah, and the only stipulation is that the 2 circles are touching one another and they're touching the line. Okay. So right now we have a point where the 2 circles touch each other and 2 points where the circles touch the line. So 1 point for one circle and 1 point for the other circle. So it's just tangent to the line.
Very good. And I understand in this problem we are interested in the little space between the circles and the line. It's how would you describe that shape?
It's kind of like, I think you could call that like, I don't know, an inverse lunoid or something.
Interesting. Yeah. That is what we're interested in this particular problem.
Yeah. And the question is, what is the minimum size of the square that is tangent to both the line and the 2 circles? So I think it'd be good at this point to talk about what tangents are exactly. And it's pretty simple. It's just it's like if 2 geometric shapes touch each other at exactly 1 point, they're tangent to each other at that point.
Correct. And in this case, if you have a square that is flat on the line, it'll be tangent all along that particular side. So it's not always only 1 point. It's also, just a given segment.
Yeah, and this square, if you think about it, if the corners are touching the circles, for example, then it could be tangent at those 2 points and wherever it is on the bottom. It could also be tangent to the side, and it could be also tangent to both a corner and a side. A way to imagine this is if you have a coin rolling off of a table with a really hard edge, right before it starts rolling off the table, you could see that the corner of the table is touching the coin, and the coin is resting on the table.
Yeah, and for the sake of this problem, this was mentioned earlier, but I think it's worth stating again. In the audience's mind, the audience is allowed to resize the square of any size at all. And essentially, the square can be rotated into any orientation, and that's actually part of this problem as well.
So, and the question is, what is the minimum size of the square? This problem was proposed in 1821, and it wasn't solved until June of last year. It was solved by Jan E. Hawley and David Crum.
That's right, and the paper can be found. We'll put the link to the paper in the show notes, so you can go through it step by step if you'd like. And I believe it was solved with a computer. Is that right?
Part of it was, yes. One of the steps involved finding Galois groups and roots and stuff. But a lot of it was done, it seems, by hand. And I think it's kind of interesting too, because it relies on this on the algorithm used being reliable, and it's an algorithm called Magma, and I believe it has been shown to be reliable.
Very cool.
So first, what we can do to solve this problem is we might be a little bit daunted because let's say the left circle has a radius of 10 and the right circle has a radius of 7. It seems like we have quite a few different configurations that the circles can be in. But we could actually, without loss of generality, we can set the smaller radius to 1 and the other one to a number greater than 1. So let's say you have a radius of like 1/2 and 3/4. Mm-hmm. You could resize that to 1 3/2. And without loss of generality, the larger circle is going to be on the right. And the reason we could do that is because if you just flip the problem around, it's the same problem.
Mm-hmm. Good. Next, we prove that for every angle that we want to rotate our square at, there's only one position in size that has the square at that angle that is tangent to the 2 circles and the line.
And the way that this was done in the paper is basically showing that if you wedge it in there, that you can't really rotate it in any way. Basically showing that it's completely wedged in there. Again, what we're going to be doing here is giving a big overview of how this is done, just so you understand, like perhaps what a long form proof is and the type of steps taken. And I think this is a remarkable proof because it takes so many steps. And it seems like it almost must take so many steps, especially when you have things like squares that are a little bit detailed compared to a circle, right?
Mm-hmm.
Like have the corners and all that. And so what this has the effect of doing is now the only parts of the problem that we need to consider are the angle that the square is at and the size of the circle on the right.
Mm-hmm.
And and that makes the problem already a little bit less daunting, right?
Yes, absolutely. In fact, the next step is simply enumerating the different configurations that exist. The paper uses the 2 points on the square touching the circle and how they are tangent to the circles that they each touch and where the tangents are. In fact, it gives a diagram of every possible orientation.
And you can imagine the ways that they are tangent. There's only 3 ways that that the paper uses for the way that they're tangent. There are points that are tangent to only a side. So this would be if like the circle touches the middle of one of the segments between the 2 corners, right?
Mm-hmm.
There's one where it's like to a side and a corner, which is like what we said earlier with the coin rolling off the table example.
Yes.
And then there's just the one where only the corner is touching the circle.
Mm-hmm.
And
that's a very, very subtle difference, but a relevant one nonetheless.
Yeah, and if my intuition is right, these authors probably tried a lot of different ways to categorize these orientations before landing on this. This is the kind of thing that you do with a big math proof, is you just kind of try different things.
Mm-hmm.
And those 3 categories aren't the only things that we have to consider.
Correct.
We also have to consider the height of the corners. So if they're the same height, that's a different category than if you have the right over left, even if the same types of corners are touching.
Yes.
So you can imagine that as being like the 2 corners touching the circles versus the square wedged at an angle where both the corners are touching the circles.
Mm-hmm. Yeah. Now I think there are 3 orientations that we have to consider here, as you said earlier. The orientation in which the 2 corners are at the same height, the orientation where the right corner is oriented above the left, and then the invert of that, where the left corner is above the right.
And if you think about it, a square is symmetric. If you rotate a square 90 degrees, you get the same square, right?
Correct.
So we only have to consider 90 degrees or pi over 2 radians of rotation, or tau over 4. Tau has the utility of being 1 full rotation versus 2 pi.
Mm-hmm.
Yeah, you start with configuration 1, 2, and 3 is what they called it. And I suppose you could start with a few other ones, but this kind of makes it neat. And the configuration 1, 2, and 3 is where the square is sitting flat on the line below.
Mm-hmm.
But configuration 1 is where both the top corners are touching the circles. Configuration 2 is the same thing, except for the left side is touching the circle also on the edge and the corner, so it's tangent right there at the corner. And then configuration 3 is where it just touched the left side and the upper right hand corner. And as you rotate the square, you get all these different types of configurations. For example, if you rotate it a little bit from configuration 3 to configuration 4, you still get it touching the side, but now the left corner is below the right corner because it's rotated a little bit.
All in all, there are a total of 19 configurations if we follow these rules. And in this paper, they are ordered by angle, and they start with configuration 1, then they go to configuration 2, and so on and so forth.
Yeah, and what's interesting too is that it's kind of a graph, meaning like you go from configuration 1 to 6, 2 also goes to 6, but 3 goes to 4 and 5 before it goes to 6. The paper has this on page 4, and it's going to be in our Patreon outline as well.
Yes, yeah. And actually, I really do enjoy the challenge of having to explain something where somebody has to envision in their mind what we're talking about. Actually, that's a good exercise.
I mean, that could almost be Breaking Math's mission statement.
Yes, exactly.
Breaking Math, making things hard for ourselves. So basically what you show is that there's only 2 valid configurations. And this was done by eliminating configurations a few at a time using some clever geometric methods. All of them are pretty much stuff that could be solved by actually Euclidean math pretty easily. So honestly, like the entire problem up to where we're going to be talking about the actual side length, a lot of it can be done by really ancient mathematics, and that's pretty cool too. That is such a recent proof with that.
Yeah. You know what's interesting is looking at this diagram, I actually thought of a way to solve this, creating a program that's sort of like a complete circuit where the light would only be on when all angles are touching. You know what I mean? And it just tried through combinatorics every possible arrangement of that square. I don't know if that's possible or not, but I don't know. Just a thought, you know?
Oh yeah, I mean, but then you run into the problem of how do you make the thing rigorous? I mean, I think that'd be definitely good for kind of like an empirical look at it, which I'm sure is what they did at some point too. Because I mean, when I've solved problems myself, a lot of times I just plug it into programs and see what everything is kind of like, and then go from there. But I mean, there's so many ways to a problem, and I've said this on the show before. But solving a math problem can be like trying to get to the store where you end up at your friend's house first, then you end up on Mars, then you end up in a universe that goes backwards in time before you finally make it to the store.
Yeah, that's true. Just looking at these diagrams, though, it looks like a rolling dice in an alley, with all these.
Oh yeah, with the square rotating like that.
Yeah. So I just thought, would there be some way to, model that? Anyways, not to take away from the paper.
Oh yeah, no, and I mean, like it could have even been that this was verified by a computer, which a lot of stuff is. But I mean, it would honestly be interesting to ask them. But so configuration 6 and configuration 19 are the only ones identified as valid. And configuration 19 is only valid when the circles are the same size. So configuration 6 is where the two upper corners of the square touch the circle, and the circle is angled towards the smaller of the two circles. So it's angled to the left. Configuration 19 is the same, but the circle is angled to the right, and it only occurs when the circles are the same size. And if you think about it, they're very, very similar, configuration 6 and configuration 19. And one more important thing is that the sides are not tangent to the circles in these configurations, only the corners.
Okay. Now, the next step is to identify what size the minimum solution is. And this solution involves magma.
Magma is a computational algebra system, which takes in like algebra and does fun stuff with it.
I'm sure it's an acronym. Is it an acronym, I believe?
Let me see.
We should look that up, see if it's an acronym. Nothing. It's actually called magma.
Yeah. Okay, so apparently it's not an acronym.
But still, that's an awesome name for a mathematical tool. Magma.
Oh, yeah. So the minimum side length of the inscribed square is the minimum value of a certain function that was identified. And the function is the square root of... So, I mean, yeah, so what does that mean, basically? It's basically that is the configuration of... That is the configuration of the square. So we already know the configuration that the square is in, and we know that it touches two sides. So this is the formula that describes a square that touches at two corners in the way that it does. And so finding the minimum side length, you have to find the minimum value of that function, and that was done using magma. And it turns out that it's a root of a god-awful polynomial. It's a 10th degree polynomial where you define 7 other polynomials. And it's f1 through f7, where it's f4 times quantity, f1 times f7 plus f2 times f6 minus 2 times f3 times f5 and quantity squared minus quantity f3 squared times f4 plus f5 squared minus f1 times f4 times f6 minus f2 times f7 and quantity squared. And then to define f1 through f7, actually, you know what? You could just find it on the paper, which again is linked in the show notes. But it's a horrible function. So now the question is there a closed form radical solution for this minimum side length?
Now they actually show the non-existence of a radical solution.
And you might think, what is a radical solution? A radical solution is just writing something down in a way that uses square roots and cubed roots and 800th roots and 24.3 roots, just things like that. It uses it uses rational numbers and roots. And division and multiplication, addition, all that. And they prove that it doesn't exist. And you might think, why doesn't it exist? Why can't you just take the root of a polynomial? Because you might remember from school the root of a quadratic can be done using the quadratic formulas. The cubic formula actually exists too for a cubic equation, and the quartic exists. But once you get to the quintic, there is no general solution, which is shown using Galois theory, which we should do one of these days. It connects group theory and field theory. Where group theory is like it shows symmetries, like, if you rotate a triangle 120 degrees, you get the same triangle and you can flip it and all that. And field theory, which is like rational numbers, the field that we're concerned with here is the field of the radicals. And you could show that this polynomial does not reduce using that. But we're not going to go into that quite because it would require an entire episode on its own. But I think it's just interesting to note that perhaps this is the reason why this wasn't found until recently, is because a lot of ancient math relies on constructible numbers in a way that doesn't involve roots.
Wow, what a way to spend a COVID quarantine.
Yeah, I mean, yeah, totally. Like, I think it's pretty cool. And again, that was solved by Jan E. Hawley and David Crum. And you can find their paper on archive.org. That's ARXIV. And the paper's reference number is 2008.00922V1 in 25th of July, 2020. And again, it'll be on the show notes.
Alrighty. That's been fun.
Yeah, and again, you should check out our sponsor, The Great Courses Plus.
Yeah, it's actually free access for a month if you guys go through our link. And actually, that's really a great way to help this show out. If you link, so.
And it's pretty cool. Like I've been using it. Like it's been pretty great. And you can do that at thegreatcoursesplus.com/breakingmath.
Yes, that's a great way to help out this show. You get a whole month for free, and there's so many topics on there. Everything from cooking to yoga to history to astronomy. I mean, what a way to educate yourself and have some great ideas for conversations at your next cocktail party when COVID is over.
Yeah, you could bypass the not being able to talk to people again because of being in our isolation.
Yep. Till next time.
Ready to level up your career? Text DISH to 44043 now to dive into a world of exciting technician opportunities at DISH. From cutting-edge technology to a supportive work environment, DISH offers the perfect platform for your success. Connect with us today to discover how you can be part of a dynamic team driving innovation. Connect today and join the DISH family, where innovation meets opportunity. Text DISH to 44043 to kickstart your journey towards a rewarding career.
With everything you have on your plate, earning your degree online seems impossible. But at Grand Canyon University, we specialize in helping you fit a master's degree in business into your busy day. Your graduation team, led by your own GCU counselor, provides you with the personal support you need to succeed. Achieve your goals with a plan and team behind you. Find your purpose at Grand Canyon University. Visit gcu.edu.